All right, good morning, everyone. Hope you guys had a nice weekend. I want to go over the calendar, which kind of highlights the what we're going to be doing these next few weeks leading up to spring break. So I just put the link under the chat box. So everything that we'll be doing is going to be coming from that AP review page. And at the top, you're going to see the calendar, which you see here. And then you're going to see every day with the notes, as well as the homework assignment handout that goes along with each notes page. So we're going to be spending these next 2 weeks just kind of reviewing basic overview of the major topics that we've covered so far, and then we can kind of delve into the more kind of specific, putting it all together. Some of the FRQs requires knowledge of a number of topics that we've covered first and second semester, kind of mixed together. But I think it's good to just kind of have everything organized to begin with, presenting you the major topics, reviewing certain topics with you, so that these next 2 weeks we'll kind of get a quick overview of everything that we've covered, and then we can kind of go back and just refine those understanding of concepts. But so first semester, we're going to do, first week, this week we'll just focus on first semester topics. Next week we'll focus on second semester topics. But along the way, I think it's important that we spend the time to practice the problems that we went over in class. So we're going to be doing front and back of a worksheet every day. But I also want you guys to spend time on the front and back of a second worksheet, a homework assignment. But I want to give you guys incentives so that when you take the time to do it, that you'll get credit for it. So I'm going to make every assignment kind of like a little quiz grade. So after all these 10 assignments, homework assignments, they'll total up to be a quiz grade, 100 points quiz grade. And I'm just looking for you to turn it in on time and to put in your effort and to check your answers with the key. But even if you miss a bunch of problems, I'm not going to take off points because you're taking the time to show me that you understand what you missed. So that's what I'm looking for. So for all these 10 assignments, you're going to be showing your work. You're going to be doing corrections in red or color ink because the key will be attached next to the student copy. And you'll be turning in both the notes worksheet and the homework worksheet. So in class, you guys just picked up both worksheets. So there's the notes worksheet that we're going to go through, front and back, and then front and back of the homework worksheets where you're going to get that additional practice. Okay. So if you want to do on a separate sheet, that's fine. If you want to attach additional sheets because the room that I provided for you is not enough, that's fine as well. But they're all going to be turned in through teams. So I'm going to be grouping assignments together. So tomorrow I'll create an assignment that just says topics 1 and 2. And then on Friday, I'll create another assignment that says topics 3 and 4. And ideally, you guys are doing this, a little every day so that you're able to submit them. But they're going to be, the first batch is going to be due next Monday. So it'll be due Monday night by 11:59 p.m. But ideally, you turn it in before that, so you're not fighting any issues that you may have with internet connection or something going wrong, if you wait till the last minute. So I'm going to encourage you guys to try to turn in, Saturday or Sunday, so that if there's any internet issues that you can resolve it and you can try it again, or you can send me a remind of that of your work. But ultimately, it's not going to kill your grade. I mean, if you turn in everything late, I mean, you can still get a 90 on that quiz grade, right? As long as you're doing the work that I'm asking you to do. So ultimately, I'm not trying to penalize you for late work heavily, but I do want to give the incentive for you guys to turn in your work on time so that you're keeping up and doing the practice, nicely spaced out, so that you can kind of benefit from all these reviews that we're doing. So next week we'll focus on integrals and differential equations, and maybe a little bit of area and volume. And then the following Monday will be the second batch of homework assignment due. And then Friday will be the last two batches, 9 and 10. Okay, so as long as you do everything that you're supposed to, it should be an easy 100 on this quiz grade. Okay, but we are going to have a second AP FRQ quiz. The first quiz is just going to be kind of homework or homework based. The second is going to be one that we take in class. And starting next Thursday, I'll specify for you, what to expect. I'll create some review worksheets, and we can, exactly what to expect from that quiz. So, that, along with this, hopefully this will help your grade. I'll also curve this quiz grade. And if students don't do well on this quiz grade, I'll probably offer opportunities for students to do corrections on it to improve their grade. So I'm not trying to, hurt your grade with these. I want to. I want these to be ones where you feel like you're getting the practice that you need to be ready for the AP exam. So that's the purpose here. Okay. Next Monday is also going to be the recovery test for chapters 5 and 6. I created a Teams assignment, so I'll hand back your test in the next day or two, and you can do corrections and do whatever assignment that is needed. I'm working on your Chapter 7 test. I hope to have that returned to you by sometime this week. And then the recovery for that, if it applies to you, it's going to be not next Monday, but the Monday after. So we'll always have a week to prepare if it applies to you, if you want to, if your grade needs to be improved up to a 79. Okay, so that is what's on the agenda for these next few weeks. Do you guys have any questions? Is there anything that that you want to have more clarity on? Okay, I think I brought this up before in this class, but just wanted to kind of repeat this. The fact that you guys do have I think there's a survey being sent out where you have a choice between either taking the exam in May, paper and pencil, or you take it online in June. And I'm gonna say that I feel ultimately it's your decision, but I think that the one in May is gonna be the one that I'm gonna encourage you guys to take. I know that there's some concerns about, oh wait, I have less resources if I take the one that is face-to-face or that is here at with the paper test. But maybe another concern is, what about all these rules that I have to memorize, right? There's so many rules, and is that going to does that mean that my performance is not going to be as good because I just don't happen to have all these rules memorized? And I think that the answer to that is yes, there are a lot of derivative and integral rules, but on the AP exam, I think they really just focus in on the ones that we see a lot of. So like power rule, e to the u, natural log. These are ones that you keep seeing over and over again. So on tomorrow's worksheet, I'll specify for you derivative-wise, there's only a couple of rules that we really need to to make sure we memorize. Chances are obscure rules are not going to show up on the AP exam, because that's not the focus of these test writers. They don't really care if you have all these rules memorized. They want to know if you can apply these concepts. Can you show your understanding applications of these concepts? So I don't think that's going to be a huge concern. And between derivative integral rules and other rules, I would say, maybe like 15 rules we got to memorize. But a lot of these you've kind of seen over and over again, so you're not really working from scratch. And also, I feel like we are kind of gearing towards that May 5th exam. So we're going to be pushing towards that May 4th exam. And so I think by then you should be ready, because we're just going to be doing a lot of practice up to that point. And the fact that you can actually go back to a previous problem that you skipped, I think that's a huge benefit that you're not going to get on the online test. So if you skip number 3 on the paper test because you want to come back to it, you can do that. But on the online test, to prevent coordination, I think, of students working together, they're going to make it where as soon as you move past a question, you can't go back to it. Whether you answered it or left it blank, that's it. So if you are on number 4 and you want to come back to it, but you can't, you just have to try your best with number 4 and then move on to number 5, because you can't go back to the previous problem. So that's going to be something to be aware of if you want to sign up for the online test. The second thing is, you got to type on the free response question, you got to type everything in. I think they're going to have notations available where if you don't do integral sign, you can push that. But the fact that you can't write things down, you got to type everything in, I think that could slow down the process, because everything is going to be through online web app or something. It's not like last year where students can take photos of their work and they can submit it. Everything is going to be through a physical website or a web app where you're going to be taking your test and submitting your test. And also something else you have to weigh is, if you want to wait till June to take that AP exam, granted, you do have additional time to prepare for it, but you got to weigh, is your motivation going to be there? Are you going to feel like you're more prepared with that extra month that we're not going to have class period to do review? Because I don't think we're going to do much after the AP exam in May. So that's something you got to weigh as well. Now, if you feel like you're able to motivate yourself, you're able to take that time to be productive, then maybe that's an option you want to consider. But if not, then if you want to get it over with, and just because we're pushing towards that May timeline, then I would encourage you guys to take that, stick with the paper test, the test that's going to be held here at Milton face-to-face. So, but yeah, I mean, I want to make sure that you guys have everything in front of you, so that whatever decision that you make, you're making it based off of all things considered. So. Okay, any questions that you guys have? Okay, so we're going to move into our first notes page, which is limits and continuity. So we're starting all the way back at the beginning of first semester. So. For those of you guys who picked up the worksheet in class, I made a typo here. So if you guys can change that for number 3 and 4, if you're picking this off the online version, I think I made the correction here. But for 3 and 4, if you guys can change, it should be approaching -3, not a +3. So -3 from the left side of -3, and then -3 from the right side of -3 for number 4. Okay, so let's start at the very top. So all the way back to limits. So what is a limit? A limit tells us the y value that the function is approaching from both sides as that function's x value gets closer and closer towards some number. So the important thing with limits is that we are more concerned about the approach than we are what's happening at that point. Okay. So let's look at number 1 here. Limit as x approaches -3. So if we want to find the full limit, we know our target is -3, but we're going to pick points on both sides of -3 as a starting point. So I'm just going to plot 2 points, choose a starting point on either side of -3. And I'm going to follow the path of the graph towards -3. So I'm going to draw 2 arrows because I'm just following the path, wherever the path leads me. And I'm going to ask myself, are those 2 arrows headed towards the same y value? Yes. And so the limit does exist, because even though the point is somewhere else, the approach is consistent, right? They're both moving towards the same y value, and that's going to be the limit. So what are they both approaching? They're both approaching what y value? 2. Yeah. So I think I had it a little bit under 2, but I meant for it to be 2. So, but the important thing is that it does exist, right? They're both headed towards the same location. But number 2, what is f of -3? Is 1. So this highlights the biggest distinction between limits and ordered pairs. There is some connection because they're both involving the same point, sort of, but ordered pair is just what's happening at that point. Limit is more what's happening around that point. So number 3, limit as x approaches -3 from the left side of -3. So what this is referring to is just this arrow on the left side, right? And here, that arrow is headed towards 2, so that's the one-side limit. One-side limit is where we just are looking at the behavior of one of the arrows. Okay. For number 4, approaching -3 from the right side of -3, that means we're following this arrow towards -3, and that's also headed towards 2. And that's another highlight that I want to specify is if your one-side limits are in agreement, then your full limit should exist. So this is just a notational way of what I did here with the arrows. Okay, the arrow is more visual, but one-side limits is more formal, right? This is how you would write out what we just drew out with arrows. Okay, let's move on to another location, another x value, x approaching 0. So limit as x approaches 0. So we know that has to be dealing with behaviors on both sides. So we're going to pick points on either side of 0. And we're going to draw an arrow towards where the graph is headed towards. So we ask ourselves, are the 2 arrows headed towards the same y value? No, they're not, right? So we can simply say the limit doesn't exist, right? We don't have a consistent movement, so limit does not exist. Okay, what's f of 0? 2, right? So the ordered pair is located here. Okay, so now one-side limit, we're just going to look at the behavior of one of the arrows. Limit as x approaches 0 from the left side of 0.
1.
Or a little bit under 1, right? So I'm going to call it 0.9, but we're just...
Say 1 minus f of -1.
1 minus f. Oh, you mean just because we don't know exactly where that value is?
Yeah.
That's fine. Yeah, but I'm just going to make an estimation. I'm going to call it 0.9, right? Because I don't, our accuracy is going to be limited by what we can see. So 0.9, 0.8. How about from the right side of 0? 2. So the important thing is that understanding, even if you put a 1 here, that's not a big issue. The important thing is that these are not in agreement, right? And because these are not in agreement, that's leading us to conclude that the limit doesn't exist. Of course, we did it from a visual arrow perspective, but this is what one-side limit tells us as well. Okay. Moving on to 9 through 12, number 9, limit as x approaches 2. So I'm going to pick points on either side of 2. And I'm going to draw an arrow towards 2. Are both arrows headed towards the same location?
Yeah.
Yes. And they're both headed towards y value of 1. Okay. F of 2 is also 1. The left arrow is headed towards 1, and the right arrow also headed towards 1. So there's something unique about this, right? Before, our cluster were not all consistent, but now it's all consistent. And this is telling us something, that if everything is in agreement, order pair, limit, one-side limit, that means the function is what? Yeah, so this is going to lead to what we're going to talk about on the second page, which is these are basically the conditions for continuity. So if you look, this graph is continuous. So that means your limit, your order pair, everything is going to line up all in agreement with each other. Okay, we have a more formal way of presenting it on the next page, but this is the idea here. So you see that when something is not in agreement, we know that it could be a hole, it could be an asymptote, it could be disconnection, but we know that if they're not in agreement, that we're not going to get continuity, right? You can tell by here, right? There's a break in the graph, there's a hole here, there's a non-removable discontinuity here, but here is the only place that we can, amongst these problems, where we're going to get continuity. Okay, so that's limit from a graphical perspective. Let's talk about limits from an algebraic perspective, where we don't have the graph in front of us and we have to rely on algebraic expressions to determine what we do with limits. Okay, so now with algebraic expression with limits, it falls into 2 categories. It's either approaching a real number or it's approaching positive or negative infinity. And we have 2 different ways of dealing with these problems, or 2 variety of steps to handle these 2 scenarios. So let's focus on real numbers first. So that means limit as x approaches 3, or limit as x approaches 0, or x approaches 5. The first thing we do is we just plug in that x value whole number. Okay, you may see a one-side limit attached to it, but no decimals. Okay, you're just going to plug in that whole number in. And when you plug that number in, you're actually gathering information about what's visually true about the graph. Because when we plug that number in, we can instantly tell, is it a continuous function? Is it a hole in the graph? Is there a vertical asymptote? Simply by looking at the result of what we get back in return. Now, if we realize that it's a real number after we plug in, if we get back a real number in return, then that's our answer, right? Our limit is going to be the same thing as the order pair, just like how we see here. But if we get 0 over 0, which is more likely, that means that we're getting a hole in the graph. Hole in the graph doesn't mean that the limit doesn't exist. It just means that the limit exists, but we just haven't found it yet. It's kind of hidden from view. So algebraically, what we're going to do is we're going to try to get rid of that hole. So we can either go through it through factoring, conjugate method, or simplifying using complex fractions. And the whole goal is to identify the hole, cancel it out, reevaluate, and that should lead us to a real number. And that real number will tell us where that hole was. Now, if what we get in return is undefined, let's say 10 over 0, or 5 over 0, 6 over 0, that means there's a vertical asymptote. If there's a vertical asymptote, our graph is going to behave a certain way. It's either go up to positive infinity or negative infinity. And if we realize that's a one-sided limit at that point, then we test using decimals. Then we do with like 2.1 or 3.9 or some decimal. But decimal is not going to be the first thing that we deal with, even though one-sided limit is part of the problem at the very beginning. So at that point, you're going to be choosing between positive or negative infinity. So write this in. I think I have it online on the new version, but then the ones that I printed out for you guys was a little bit older there. So we want to choose between positive and negative infinity, assuming we've gotten to that point where we realize that it's like a 10 over 0, vertical asymptote, and it's a one-sided limit. All right, so we'll practice with real numbers, but we have a completely different set of rules for infinity or approaching negative infinity. And we compare degrees. Okay, we don't plug information in anymore. We just we seek the highest exponents between numerator and denominator, and we compare them. If your denominator has a higher degree, then your limit is always going to be 0. Okay, if your numerator and denominator are equivalent in degree, then our limit is just the ratio of the coefficients. But if your numerator is greater than your denominator, then your limit doesn't exist. Okay. Now, there is another way of dealing with real numbers. So going back to algebraic steps, approaching real numbers, is if you get 0 over 0, you can go through factoring, conjugate methods, complex fractions, but those are very specific, right? Very specific cases. L'Hopital's rule, we didn't do this until after our unit 1 because we haven't learned about derivatives yet. But now that we know derivatives, I'm putting it with the limit content. And it's the fact that if we get 0 over 0, we can use derivatives to help us produce a different form, which we can then reevaluate. So the way we do that is we take the numerator, we find the derivative of the numerator, and then separately we find the derivative of the denominator. And then that will allow for a new form to arise, and then we reevaluate that new form, and that should take us to a real number. But we can only do L'Hopital's rule if we realize it's 0 over 0. If it's any other situation, we're not going to be able to apply L'Hopital's rule. Okay, so let's start with number 1, and we can kind of see when some of these apply. All right, so limit as x approaches 3 from the left side of 3 into our expression. Okay, first things first, what do we do?
Plug in the x value.
Okay, just the 3, right? Yeah. No 2.9, no 3.1. We just want to see what's happening at that whole number. Okay, so 3 goes in first. And what do we get?
0 over 0.
Okay, 0 over 0. So 0 over 0 means that there's a hole in the graph. We can't say the limit doesn't exist, right? Because if there's a hole in the graph, the limit does exist. We just haven't found it yet, just like how we did with number 1. But we have a couple of options here. We can go through factoring method, which works, but we can also go through what? L'Hopital's. So I'll do both ways, and you can kind of see how they're going to line up. You can choose either way to get to your limit. I'll do the factoring first. So the numerator will stay as x minus 3. The denominator multiplies to be negative 3, adds it to be negative 2. You see the whole emerging fact, the x minus 3 is what's causing that 0 over 0 to occur. There's something left up top though. What's left up top? A 1. Okay. So let's reevaluate. Okay. Again, just the whole number, right? No decimals. There's no need for decimals here. So just the 3 in for x, and what do we get? 1/4, right? 1 over 3 plus 1, 1/4. Okay. So that's one way to find the limit. A second way, because we get 0 over 0, we also have a condition necessary for L'Hopital's rule. So let's ask ourselves here, what's the derivative of x minus 3? Just one, okay. What's the derivative of x squared minus 2x minus 3? Okay. Okay, we now have a simpler version that hopefully should not give us 0 over 0 anymore, and we reevaluate. Plug 3 in for x. And what do we get? Same thing, yeah. So you have some options dealing with limits, but L'Hopital's rule is just more robust, right? It can handle a wide variety of situations, but factoring is only going to be very specific. But ultimately, you may sometimes have multiple options for limits. Okay, questions with one? Okay, number 2. Again, limit with a one-sided limit, but what's the first thing we do? Just the -3, right? No decimals. All right, let's see what happens here. And we get -5 over 0. You're right, it's undefined. But I want to kind of give a visual perspective here. What's happening at -3 for this graph? If you were to see the graph in front of you, what's happening there? Vertical asymptote, yeah. So I want us to picture that. There's a vertical asymptote here. And we know that with vertical asymptote, our limit is never going to exist at a vertical asymptote, right? Because the graph is never going to move towards the same y value, not a real number y value. So we know the full limit doesn't exist, but I want you guys to visualize what's happening here, right? So imagine a vertical asymptote. Right, there's only 2 ways that a graph can behave around an asymptote, right? It's either going to go up or it's going to go down, right? And maybe my arrows may be flipped around on either side, or maybe they're going toward the same direction, but it's one of those 2 options in terms of the direction of either side. So we know the full limit doesn't exist, but now we go back to the problem. Is it asking for a full limit? It's only asking it from one side. So true, the limit doesn't exist, but this is asking for the behavior of just this one side, right? We know the limit doesn't exist, but the one side limit does exist, right? It just wants to know, is it going up or is it going down to -infinity? So now to decide between those 2 choices, we can now rely on what? Decimals, right? So this is where decimal come into play, not any earlier, right? There's only a very specific situations that we deal with decimals, and it's only at this point when we realize, okay, limit doesn't exist, and I'm asking for a one-sided limit, and I'm choosing between positive or negative infinity. So we're going to test the decimal here. So what's the decimal value that is to the left side of -3 that is close? Okay, yeah. Yeah. Now, decimals feel messy, I know, but really, when you plug in, all you care about is my fraction going to be positive or is my fraction negative? If my fraction is positive, and I know my one-sided limit is going to be positive infinity. If my fraction is negative, then I know that my one-sided limit must be negative infinity. Okay, so -3.1 into my original expression. Okay, numerator, what? -6.2 plus 1, that's still going to be negative. -3.1 plus 3, that's also negative. So negative over a negative, positive, and so that is where decimals help us out, only for this very specific case where we realize that there's a vertical asymptote causing this issue. Okay, any questions with 1 or 2? Okay, what's different about number 3?
No approaching.
Yes, no longer approaching a real number, right? It's approaching infinity or negative infinity. And how do we handle infinity or negative infinity? Yeah, we find the highest exponents and we compare them. So what do you notice for this problem? Yeah, they're the same. So we're just going to be zooming in or zeroing in on that x squared and negative 5x squared. We don't care about the rest of the expression. So because the degrees are the same, what's going to be my limit?
1
Over 1 over negative 5. Yeah. So the 1 is the number attached to the numerator x squared. The negative 5 is the coefficient below. So we just put them over each other. 1 over negative 5. It's not hard, but it does require us to understand, the different perspective in dealing with infinities, right? We don't plug infinity in. We jump to this other method. Okay, questions so far? All right, number 4. Number 4 looks messy, but that's not going to change our approach, right? First thing we do, yeah, plug in 0, right? Let's see what happens, right? Maybe it's already going to give us a real number. If it does, then we can stop. But if there's something else, we can deal with it. So okay, let's see here. What's sine of 0? 0, yeah. Denominator here, 2e to the 0. That's just going to be 2. 2 minus 1 is 1. What's natural log of 1?
0.
Also 0. So 0 over 0, we know there's a hole in the graph. But we're kind of restricted here. The only method that's going to work for this is what? Yeah, L'Hopital's. This is going to be tough, right? There's nothing to cancel out. There's no factoring that we can do. It's not conjugate. It's not complex fraction. So we're forced to have to go through L'Hopital's. But we did confirm that our condition is met, right? If we're getting a different scenario, we can't do L'Hopital's. It needs to be 0 over 0 if you want to do L'Hopital's. So that means we have to take the time to find the derivative of the expressions that we see in front of us. So as a reminder, sine's derivative is cosine of u times u prime. Natural log's derivative is u prime over u. And there's one more, is e to the u. E to the u is just the function itself times u prime. Okay, so I'm going to use the space under number 3 because I'm running out of space for number 4 here. So limit as x approaches 0. We'll take the derivative. Sine becomes cosine. And now I'll take the denominator's derivative, the natural log of u. So there's my u value. My u value is inside the parentheses. So what do you think my u prime is going to be? What's the derivative of 2e to the x? Yeah, just 2e to the x. And that 1 goes away, right? Okay, so I'm going to put that here, 2e to the x. All over my original u value. So I'm just going to copy down my parentheses here, 2e to the x minus 1. Now, this looks messy, but really, we have the derivative form. We're just going to plug 0 in and see what we get. And hopefully, this will lead us to something other than 0 over 0. Okay, cosine of 0 is 1. Yep. 2e to the 0 is just 2. 2 minus 1 is just 1. So 1 over 2 is just 1/2. Yeah, and that leads us to a real number. So L'Hopital's rule is able to help us take us from 0 over 0 down to a real number. Okay, so I hit kind of the big scenarios involving factoring or L'Hopital's rule, where the limit doesn't exist, but we have to go through the additional step of testing decimals. Completely different scenario with infinity, and then being forced to have to use L'Hopital's rule. So there's more for you guys to explore on the homework sheet, but hopefully you guys will get that practice in after we've gone through these together. Okay, any questions? Okay, let's go to second page. Okay. We talked about continuity conditions and demonstrated it how what's going to occur if a function is going to be continuous. But we have a more formal definition here. So let me go through the definition and then we'll practice them. So the first thing is f of c is defined. Does the point exist? So let me just draw another diagram here. Okay, so the point exists. Let's say this is what the graph looks like. Does the limit exist? So that means, is the graph approaching the same y value from both sides? And let's say the graph looked like this. So this would pass the second condition, right? Because if I choose points on either side of C, and if I move towards C, they're both headed towards the same destination. So first condition passes, second condition passes. But the third condition, does the limit live where the point lives for this graph? Okay, so this one would fail. But you can imagine what a full condition passing would be, right? It would be where the point is lining up nicely with the hole. If it does, then all three conditions would pass, and if all three conditions pass, then we can safely say our function is continuous through that point. And for every one of these problems, we're just going to be stepping through these conditions and seeing if they're all aligned. If they're aligned, then great. If they're not aligned, then we'll say, okay, it fails here. That's why the function is not continuous. Okay, so let's look at number one. We have our function defined as square root of 25 minus x squared, but it's being split, right? We have a g of x where we have the square root on one side, but then we have x plus 7 on the other side of -3. And we want to know, is the function continuous at -3? So we're going to go through these conditions to see if everything is lined up for us to conclude whether the function is continuous. All right, so just to give you a visual here, we got the square root and we have a linear graph. So maybe a graph that looks like this. The square root is going to kind of look like a semicircle, or at least a part of a semicircle. But then the x plus 7 is just going to be a linear graph with a positive slope. And we just want to know, are those two graphs going to line up at -3? And we're going to be able to determine that just by stepping through our continuity conditions. So first condition, our C value is always going to be provided for us. In this case, our target X value is -3. So we want to find what is the value of G of -3. So we just follow the definition here. G of -3, let's see, where is -3 defined? Is it with the first piecewise or with the second piecewise? First one, right? Because we see the less than or equal to. So we know that -3 is going to go into f, and f is defined as square root of 25 minus x squared. So we're just going to follow what is defined here. (25 minus 9 is 16, root 16 is 4. So we have that squared away, and we can move on to our second condition. Does the limit exist? Well, the issue is that we're looking at both sides of -3, and we see that on both sides of -3, we're dealing with two completely different functions. So we're going to have to rely on two separate limit statements to see if they are lining up and moving towards the same y value. So we'll do a limit as x approaches -3 from the left of -3. So we want to figure out the behavior on this side, which is obviously dealing with the square root. So I'll put the square root expression for the left side of -3. And then from the other side of -3, it's a completely different function. And that is with the x plus 7. So I'm going to have a limit statement for that function as well. Evaluate -3. And for the first one, again, the one side limit is just there for notation. We're not going to do anything with decimals. So 25 minus 9, same thing as above, is 4. How about the second one here?
Equals 4.
Also 4. So that's a good sign. One side is headed towards 4, the other side is headed towards 4. We should be able to conclude that the full limit exists, right? Because we have these two arrows in agreement. So first condition passes, second condition passes. Is the third condition going to pass?
Yes.
Yes, because third condition is just looking back and comparing the results from the first two. So the point is living where the limit lives. So we can say g of -3 is equal to the limit everything's in agreement. We can conclude, therefore, our function is continuous at x equals -3. All right, questions with 1.
Yeah, I have a question.
Okay.
How did you know that g of -3 was equal to f of -3, like way at the beginning?
Oh, with condition 1? Is that what you're asking?
Yeah.
So -3, we know -3 is defined with the first piecewise because you see the less than or equal to.
Yeah.
But it's only less than for x plus 7, so it can't refer to the x plus 7. So we got to plug -3 into f of x. And f of x is defined above here.
Okay, so because x plus 7 is only less than,
Exactly.
not less than or equal to, you can't use it?
Exactly. Yeah, we're looking at that notation to help us decide which one to plug in.
Okay, that makes sense.
Okay, good. All right, any other questions with 1? All right, number 2. If a function is continuous for all real numbers and our function is defined when x doesn't equal to -2, then f of -2 equals. So we see the word, if you see the word continuous, I'll just go through the continuity conditions. But I do want to point something out here. When it says x equals does not equal -2, this means that this function exists everywhere except -2. Or our function is f of x is defined everywhere. Except at -2. So that means on the left side of -2 is this function, on the right side of -2 is that function as well. Okay. But let's just go through our conditions here. First condition, we know the target x value is -2. We want to find out where f of -2 is. But that's what the problem is asking for, so we're going to have to leave that blank. We don't know what that is, but we can always come back and refer back to it, right? But at least we're just going to at least have some format going, right? We're just going to follow what the condition says, and we can kind of figure out what's missing. Thank you. Okay, so moving on to the second condition, because this is unresolved. Does the limit exist? Now, this case, we don't need two one-side limit. All we need is one limit statement, because this function is the same function on either side of -2. You see how previously we have two differently defined functions on either side of my target? Here, it's the same function on either side, so I only need to rely on one limit statement. All right, so this is kind of like a mini problem, right? We want to find the limit of that expression. And what can we do first? Yep, plug -2. Let's see what we get. And what do we get?
0. Yeah, 0 over 0.
0 over 0, we know there's a hole. Again, you have two options. You can either factor or L'Hopital's rule. Either way, we should be able to get down to a real number. Okay, I'm going to go through factoring, but L'Hopital's rule works. The hole goes away, reevaluate, -2 minus 2 is -4. Okay, so the limit is at -4. So in order for the third condition to pass, what needs to happen?
They need to equal. Like the limit needs to equal.
Yep. And so f of -2 must be equal to the limit as x approaches -2 of f of x. But in order for that to agree, I need everything to be lined up with -4. And because of that, we can kind of go back and say, well, f of -2 must be equal to -4, because that's the only way that I can get everything to be lined up. And because I'm trying to fulfill continuity conditions, that's why I know I need everything lined up. Okay, questions with 2? Okay, yes, question.
Just why how do you know that first condition before we assuming that all the
We know it's -4 because it says that it's continuous. So that's forcing us to come up with something that will allow everything to work. So the fact that it's continuous is kind of forcing our hand here. We're kind of, we're restricted. This number has to be -4. Otherwise, we're not going to be able to get everything lined up. Okay, a few minutes here. I want to kind of go through this final topic, intermediate value theorem. It sounds complicated, but really, let me just kind of read the definition here. If a function is continuous, we can guarantee a specific y value on the graph if one endpoint is below the y value and the other endpoint is above the y value. So if I'm trying to guarantee a specific y value, I just need one endpoint to be below it and the other point to be above it, because I know the graph has to connect through that point somewhere if it's continuous. Okay, so there's no calculus here, which is kind of logically visualizing what must be true. So here it says our function is continuous on the closed interval. So they did tell us it's continuous. We know that we're not going to be dealing with any jumps or breaks or asymptotes or holes. And they're giving us two endpoints here. We have order pair -3, -1, and we have order pair 6, 3. So what can we guarantee about what lies between? So I think The nice thing about IVT, well, the helpful thing about IVT is if you can sketch it out, you can convince yourself visually. So one endpoint is -3, -1. The other endpoint is at 6, 3. So no matter how I draw the graph between it, I know that my graph is going to be connected, right? There's no breaks. So I'm just going to create a situation. Doesn't matter what I do. But here's an example, right? Now, based on IVT, what can we guarantee? Can we guarantee that f of 0 equals 0? Well, actually, not the slope. Well, the slope is something else. The slope is going to be MBT, which we're going to deal with later. But right now, we just, what can you guarantee, though? Can we guarantee that every y value between -1 and 3 is going to be reached sometime in that interval? Yeah, should be, right? Can you create a situation where these two graphs connect, but then you skip a y value somewhere between? If it's not continuous, you can't, but it's already stating it's continuous, so, right? There's no situation that we can create. So every y value is hit, right? If you throw out a number, no matter how complicated that number sounds, let's say you choose like 1.956. Right, that's guaranteed, right? 1.956 is going to be guaranteed here. So I think our answer is going to be C, right? Every y value is safe between -1 and 3. I think D is a very specific case of IVT. We can guarantee a y value of 1, but I think C is kind of encompasses a broader situation of what we can guarantee. F of C equals 0. Okay, we can't guarantee 0 between -1 and 3 because we're looking at x values between -3 and 6. Okay, so D is partially correct, but I think C is a better answer. All right, so we've gone through the major topics for limits and continuity. Hopefully, guys, you'll have spent some time starting your practice worksheet, and I have the key attached. So after you guys try it, or if you're stuck, feel free to look at the key and help you along. But just show me that you're attempting it through your work. If you made a mistake and if you do it completely wrong, still include that in your even if it's completely wrong, if you just show that to me, it just demonstrates that there's proof that you attempted, that you did something on your own. So I want to see that as well. Okay, thanks everyone. Hope you guys have a great day. See you tomorrow. We'll start derivatives tomorrow.